Hello everyone, today I'm going to show you how to successfully pick the delta in the epsilon delta definition of limit. So most often in calculus 1, you will encounter a problem that asks you to prove that the limit of some function f of x is some value L as x approaches some real value x0. Now the epsilon definition of limit means that you will need to prove that for every epsilon greater than 0. So this notation is a shorthand for the word for every. There exists, so this notation means there exists delta greater than 0 such that whenever x is close to x0, and that is captured by the notation x minus x0 absolute value less than delta greater than 0. The greater than 0 is in fact just to let everyone knows that we actually don't care when x is exactly x0. The function may be nasty, may even not defined there. What we need to care for is when x being close to x0, but not equal to x0. Whenever x satisfies this inequality, this immediately implies that f of x will be close to the value L. So in other words, the difference between f of x and L absolute value means the distance between them has to be less than epsilon. Now most of the time, x0 is given. The value L is also be given or can be anticipated or can be guessed easily. The function is also be given. And although epsilon is arbitrary, but sometimes some professor can give you some specific value of epsilon to start to play with. So this value can also sometimes be given. But you should be prepared for the fact that no matter what value of epsilon is given to you, you should be able to pick delta. You should be able to choose and point out what delta is. Right? So these epsilon are sometimes be given. I put them in the parentheses, means that sometimes, sometimes not. You should prepare for the worst case. Now, the deal is, for any epsilon, maybe nice, maybe bad, you don't know, maybe really, really nasty, for any really, really nasty epsilon given to you, you should be able to show that there is some delta that will make this happen. If you can show or if you can point out such delta, then the limit is L. If you cannot point out the delta because of the fact that no such delta can exist, then the limit is not L. So let's put it this way to help you understand better what is going on here. So this is like a game in which you are going to let your worst enemy choose the epsilon. Of course, he or she is going to pick the worst possible and keep trying until he or she can kill you. Your job, this is what you can do. This is your choice. So your job is to choose the delta so that this will happen. If you can choose the delta to make this happen, then you survive and the limit is L. If you cannot survive, the limit is not going to be L. Right. Let's consider several examples to make it clear. So suppose we are asked to prove that the limit of x minus 1 squared is 0 as x approaches the number 1. So if you want to prove it by epsilon delta, then you will need to first rewrite the definition. This is the definition. You need to rewrite the definition with f, L, and x0 being replaced to make it fit to the context of this specific example. So you need to show that for every epsilon greater than 0 given to you, there exists a delta greater than 0, meaning that you can always choose, right? You can always choose the delta so that or such that whenever x and x0, which is the number 1 in this case, whenever they are close to each other, and being close means less than delta, and we wouldn't want to care about x equals to 1, then this inequality would immediately imply that f of x, which is x minus 1 squared, minus L, which is 0, you need it to be less than epsilon. In other words, you want this to be less than epsilon, right? You will need to choose an appropriate delta to make this implies this. There's going to be a box. You will choose the delta, put it into the box to show that you can always do so. Now the key is that you will need to unfold the secrets in between this inequality and this inequality. Alright, so although we write it as an arrow, but there's actually a lot in between them. In order to do so, we are going to use something that I call tracing back method. And by tracing back method, I mean that instead of writing this, I'm going to ignore it and write it down at the bottom. Alright, so this is what I want to get. Okay, after we simplify the subtraction by 0, we should be able to get this. If you can get this, the limit is going to be 0. Now the fact is that it's not straight going from this to this without any reasoning. There are a lot of reasonings in between them. And so we are going to trace back this way. If you want this to happen, isn't it that you just need x minus 1 square to be less than epsilon? That's it, because the square is always positive. If you want this to be less than epsilon, if you want the square to be less than epsilon, it just means that you only need the absolute value of x minus 1 to be less than square root of epsilon. If you have this, then you immediately have this. You just square both sides. Now, it comes to where you are going to choose the delta. If you have this, then you would get the conclusion. But the fact is that you don't have x minus 1 less than square root of epsilon. What you have is x minus 1 less than delta. So in order to make the connection from here to here, you will need to choose the delta so that this implies this. And a very simple choice is to make delta equals square root of epsilon. If you do so, because delta is equals to square root of epsilon, having x minus 1 less than delta is the same as having x minus 1 less than square root of epsilon. And then you just square it, and then you just make the absolute value, and then you get to the conclusion. And we are done by the choice here. Now, if you are given, say, if your professor is nice and he or she is giving you epsilon being 0.01, then the delta you would need to pick is square root of 0.01, which is 0.1. If someone else gives you epsilon to be, say, 4, then you only need to pick delta to be square root of 4, which is 2. And no matter what epsilon values that you are going to be given, say 0.0001, then you only need to take the square root, and that is going to instantly give you the delta that you need. Alright? And even your worst enemies, who is going to choose a very bad epsilon for you, you can still survive by using this formula that you have found. And that's the idea. The limit exists and equals to 0 in this case. So now let's consider another example. prove that the limit of 2 to the x minus 2 equals to 0 as x goes to 1. Then that means you will have to rewrite the definition for this specific case. So for every epsilon greater than 0, there exists, or you should be able to choose a delta greater than 0, so that whenever you have the inequality x minus x0, which is 1, less than delta, this inequality immediately implies the absolute value of f of x, which is the given function, minus L, which is 0, less than epsilon. Alright, and as I said before, there are many things happening in between this inequality until you can get to this inequality. So we are going to first pretend like we don't have this inequality, and our job is to try to choose the delta, right, such that this will finally implies that 2 to the x minus 2 minus 0, we wouldn't need it, so we need this, less than epsilon. Alright, so you observe that you will need to get something similar to this, right, so that you can start choosing delta appropriately, just like what we did in the previous example. We end up having something similar, and then we pick the delta based on the reality. Right, so similar thing will be happening here. You want this, but it is going to give you something with x. However, you want x minus 1. The key is to try to relate to x minus x0 from the function's inequality. So in order to do so, we first divide both sides by 2. Doing so will give you this inequality. If you have this, you have this. Of course, you just multiply by 2 to get this. Now, if you want this to happen, it is the same as, and if you want this to happen, it is the same as, so this is a negative quantity. This is 1 plus, so that is greater than 1. So this is a positive quantity. So if you have this, then you have this. But how can you get to this? Well, if you can get absolute value of x minus 1 being less than the minimum between the log base 2 of 1 plus epsilon over 2 and the absolute value, we use absolute value because we want it to be positive, right? The absolute value of log base 2 of 1 minus epsilon over 2. If you have this, then it will immediately give you this. Now you compare and you say, well, we end up having something looks very similar, right? The left-hand side exactly the same thing. Now, if you want this to imply this, you only need to pick delta to be exactly the right-hand side. So pick delta to be the minimum. So let's consider a value for epsilon. If epsilon, say, being 0.1, then you will only need to pick delta to be the minimum of log base 2 of 1 plus epsilon over 2, which is log base 2 of 1.05, and the absolute value of log base 2 of 1 minus epsilon over 2, log base 2 of 0.95, absolute value. And I computed. This is about 0.070, where the other is about 0.074. So you know that this is the smaller value. So then delta has to be 0.07. And that's your choice corresponding to the given epsilon to be 0.1. If your worst enemy changes the choice for epsilon, you can just use the formula you develop here and pick the appropriate delta. You will always be able to survive regardless of the choice of epsilon. And so the limit is 0 in this case when x approaches 1. So as you can see, the key is right here. When you can relate the inequality of the function back to x minus x0 in some way, and then you solve for x minus x0. So you see, we just try to solve for x minus x0, x minus x0. And then once we get to the form where the left-hand side of what we started, exactly the same as the left-hand side of what we currently have, then we just pick delta to be exactly the right-hand side. Well, the fact is that you can pick delta to be 1/2 of the minimum, because less than 1/2 of the minimum implies less than the minimum. And so the fact is that you can pick delta to be any number that is smaller than the minimum here. But for the simplicity purpose, people always pick delta to be exactly the same as the number appears on the right at this step. Now let's consider another example in which pulling out x minus 1 is tricky. Example number 3. Prove that the limit as x goes to 1, again 1, of the function sin of 2 pi x is equals to 0. Again, you have to first rewrite the definition to see what you need to prove, right? So you want to prove for every epsilon greater than 0, there exists delta greater than 0, such that whenever x minus x0 less than delta, you immediately will get the absolute value of the function minus the L, which is 0 in this case, has to be less than epsilon. Again, I'm going to pretend like this appears way down below. Alright, so let's write it here. Minus 0 means nothing, right? So less than epsilon. Alright, and we are going to work backward to be able to choose the delta. Alright. Now let's unfold the secret in between the top inequality and the bottom inequality. Now if you solve this one, you will end up getting something related to x only. But what you need is x minus 1. So somehow at first you will try to create x minus 1 by using some mathematical laws and rules. Now the fact is that sin function is a 2 pi periodic function. So you can add 2 pi or subtract 2 pi. That will not change the value of the function. So you would have this if you have sin of 2 pi x minus 2 pi absolute value less than epsilon. This is the same as saying, right, once you have this, you have this. It's just distribution of 2 pi into the difference here. Now, you are going to get this if you have less than epsilon and greater than negative of epsilon. And you would have this if you have 2 pi x minus 1 less than the sin inverse of epsilon and greater than the sin inverse of negative epsilon. Because sin inverse is an odd function, this is the same as minus sin inverse of epsilon. And you could have this if you have x minus 1 less than sin inverse of epsilon over 2 pi. and greater than negative of sine inverse of epsilon over 2 pi. You would have this if you have the absolute value of x minus 1 less than sine inverse of epsilon divided by 2 pi. And now there you go. You see that the left-hand side and the left-hand side are similar. So you can just pick delta to be this guy. Now if delta equals to sine inverse of epsilon over 2 pi, then x minus 1 less than delta immediately means that x minus 1 less than the sine inverse of epsilon over 2 pi. And then the whole process that you worked backward will now give you the direction to the conclusion. So suppose that you are given epsilon to be 0.5, which delta are you going to choose? Then we just need to pick delta to be the sine inverse of 0.5 over 2 pi, which is in this case pi over 6 over 2 pi, which is 1 over 12. Now if you are given another epsilon value, you will need to plug it in here, use your calculator to get the value out and divide by 2 pi. Of course, that can be not as beautiful as this number, but that's the way we are going to get it. Okay. Thank you for watching.